Today I'm going to show you guys how to use the ideal gas relationships of PV over NT equals P2 V2 over N2 T2. I'm going to show you how to not use algebra and solve for the variable out of this whole bundle, but rather use the relationships between pressure, volume, number of particles, and temperature to make a unit multiplier and conceptually flip or flop the relationships to get the outcome that you conceptually know you need to have occur. So I'm going to use the example on the left to start this. If you imagine a sample of gas that's at 280 cubic centimeters of volume, and that gas is at 103.7 kPa of pressure, and it was allowed to cool to 288 Kelvin, which resulted in it being at 99.8 kPa of pressure, and then that volume actually decreased to 145 centimeters cubed. If you had to predict the initial temperature, you would have to come over to this equation with all these relationships and take initial temp, rearrange it algebraically and isolate it, and rearrange everything else over to the other side, and then you could complete the algebra. And that's totally fine in some cases, but I'm going to show you guys how to do a conceptual setup with the unit multiplier strategy. But first I'm going to use my graphic organizer to plug in the information I know and then try to make sense of what changes are occurring. But I'm already noticing this is different from a lot of problems you might see in class. We're predicting an initial temperature. So we almost have to work backwards from final to initial when thinking about the change versus the way we've been predicting the final result of volume, temperature, number of particles, or pressure. So it's going to be a little bit of a reverse process here. So initially we know the volume is at 280 centimeters cubed. And for this organizer, I don't really care about tracking the units, but I will during my unit multiplier. The pressure initially is at 103.7 kPa. We also know that it's allowed to cool to 288 Kelvin. So I know that's the final state, so I actually have to put 288 in the final. And then that pressure becomes 99.8. And that conceptually makes sense because if you cool the gas, the particle speed decreases, force of the collision on the surface area likely decreases at that point too. Now I know I also want to get temperature initial, so I'm going to actually put temperature initial as Ti, as T1. I also know the volume decreases to 145 cubic centimeters. And I'm going to assume that the problem maintains constant number of particles. So I'm just going to dash those out. So now we need to go through and do the change in column. Now because this is asking for an initial temperature, we have to think backwards. So the change I'm going to fill out is actually for the final to the initial, unlike what we had done previously in class for most of the problems. So from 145 final back to the initial, that's an increase if we reverse this. When I look at the pressure ends up at 99.8, but originally is at 103.7. So if we think backwards, technically that might be an increase if you think backwards. Next, you need to think about what the effect is on the unknown temperature. So think about what must have happened to the temperature. So if the volume increased to get back to the initial, then what must have happened to the temperature? If you can't think about that conceptually, think about the data, the basic sketch of the graph for the volume temperature graph in Kelvin. So volume increased, doing the reverse engineering here. If volume increased, what must have happened to temperature under those circumstances? In order for volume to increase, temperature must have increased also. So I'm going to put INC for increase. If you look at the pressure has increased if you reverse engineer this and go back from final to initial. So what must have happened to temperature for pressure to increase? If you can't conceptually think about that, think about the graph for pressure and temperature. It's also a linear pattern. So if pressure has increased along the y-axis, temperature must have increased. So it must have been larger in the initial state for this change to occur. All right, so remember, we're doing this in reverse so that we can get the initial state of the temperature. Now, out of all the data, we only have 288 Kelvin, but we're missing that partner in crime with the initial temperature. So I'm going to start my unit multiplier off with the lone solo temperature that we're missing the partner in crime to. So if I start off with 288 Kelvin, and I'm just going to go down the list based on reasoning, based on algebra, and rearranging the original combined gas law relationship over here, I'm going to go ahead and flip-flop 280 and 145 centimeters cubed as needed to get the effect. So in order to get the proper effect, to make an increase on temperature, I actually have to put the 280 in the numerator rather than the 145, because if I put the 145, that would decrease the overall number across the top and not increase it like the effect we conceptually said is going to happen. I'm going to make sure I put my units on here and track those. All right, so that ratio's done. Now I'm going to use the pressure ratio and the effect on the unknown. The unknown is temperature 1. So we said that if you go from final to initial, the pressure increased. And if the pressure increases, the temperature must have increased. So we got to make sure we set up the 103.7 kPa and the 99.8 kPa so that we end up with a larger increase rather than a decrease. So I'm going to stick the 103.7 kPa in the numerator and the 99.8 kPa in the denominator. The whole point to setting these up with the larger number in the numerator is because we know that the change in volume in reverse leads to an increase in temperature, or at least the temperature must have been greater in the initial state conceptually. Now, if you guys multiply along with me, you can pause the video and check this work or think about the questions that I've already gone over. If you multiply across the numerator, I get the following numbers, and then if I multiply across the denominator, I get the following numbers. So numerator, I got 8,362,368 Kelvin. Assuming I typed that incorrect, that's what I got. If I multiply across the bottom and do not take 288 Kelvin times the bottom, there's a ghost 1 hanging out under the 288, so do not do that. If I take 145 times the 99.8, I should get around 14,471. Now the reason why I'm not putting units on the denominator is because these cubic centimeters have canceled and the kPa have canceled. And if I simplify this ratio by dividing it, I should get 577 Kelvin. So that's what the initial temperature should have been. And that should make sense conceptually. If you were to plug in 577 and there's a decrease in temp, most people would agree that if you decrease the temperature, the volume should decrease, which the graph suggests from our original data. If you had a temperature decrease, the pressure should decrease, which is suggested by the pressure-temperature relationship. As temperature decreases, the pressure should decrease. So conceptually, that makes sense. I'm going to pause the video and reset on a second problem, and you can follow along also. Before I move on to the second problem, I do want to show you guys how you might represent the sample of gas with particle diagrams, and I will show you guys the microscopic sample version of a particle diagram, and then possibly the macroscopic change where we kind of fudge what a particle diagram really represents, but as a macroscopic sample since there's a volume change. So the sample of gas, let's just pick 2 particles, and then I'm going to put my average EK arrow to represent the temperature at that moment. And since I calculated it's warmer in the beginning, initial state, I'm going to make that arrow longer. So what I want you guys to think about, if I were to zoom in to a tiny microscopic volume and keep that microscopic volume approximately the same volume as best I can draw, I have to think about after the volume decreases according to the graphic organizer table, I have to also think about what does that look like if I took a microscopic sample of that gas again. Since the volume decreases overall, that means that the particles are jammed closer together, and there's an increase in density and gathering of those particles, and the space between them has decreased. So you might draw that same microvolume with more particles in that same microvolume. We haven't changed the number of particles, but if you took the overall volume and zoomed into the same microscopic spot and you allowed that volume to decrease overall, you would see more particles inside that window. And since the temperature decreased, I would actually change my average EK arrow to be less. Now, some people might prefer to try to track the macroscopic change in the volume. So from 280 to 145, macroscopically, that whole sample of gas decreased volume. So instead of doing just a microvolume, which this is a microvolume of a much bigger sample, some people might prefer to draw a micro volume, but actually treat it like a macroscopic change for the overall volume. So some people might think that this volume in the beginning is 280 milliliters and that it decreases to 145, but since it's kind of macroscopic, you simply just track the same original 2 particles. And I'm okay with that. The only danger is for changing the microscopic volume into a macro version is that if you ever had the number of particles change as well, it gets into a funky situation where changing the volume window and the number of particles is weird. So you might just stick to using the same microscopic volume when changing the number of particles. So pause the video, think about those decisions and why I made those choices, and then you can move on to the next example problem with me next. All right, in this second example, we're going to look at a bike tire, and we're just going to make some assumptions about the bike tire. I know that the bike tire can have some expansion, contraction, and some stretchiness to it. We're going to kind of ignore that stretchiness and just focus on making a general judgment about the changes that are taking place with the gas inside the tire. So carefully read this problem with me and think about how we would plug in that information and how we need to start thinking about the changes that occur that might have an effect on the unknown value. So if you imagine there's a bike tire inside a 22-degree house, and right off the bat I recognize that these relationships over on the right that we got from class, the algebraic relationships, the temperatures must always be in Kelvin. So I've given permission to just take a shortcut and just add 273 to any Celsius that you're given. So we'll have to add that to the 22 degrees Celsius at some point. So imagine you're inside a cool house at 22 degrees Celsius and the tire is currently holding 300 milliliters of air and containing 10 amounts of gas particles. A bike pump pressure gauge initially reads that the tire is at 98 psi. If 5 more amounts were added to the tire for a total of 15 amounts, I want you guys to estimate what the pressure would be if the bike was also brought outside in 35 °C weather. So there's a lot going on here, and that's why you guys should take advantage of the graphic organizer. Okay? And then there's a problem at the end that says, hey, does the tire pressure get beyond the maximum pressure of 125 psi? And we can look at that at the end and then try to do some particle diagrams. So I'm going to organize my information in the graphic organizer. I know in the beginning state that the volume is at 300 milliliters of air and the temperature is at 22 °C. But if we add 273 degrees to that, we should get 295 Kelvin. The number of particles in the initial state, we're assuming there's 10 amounts of particles that have already been added at some point in time, and that's what the tire currently has in it. The pressure, while it's in the house, is 98 psi. In the final state, we added 5 more amounts of particles, so we have a total of 15 amounts of particles in the tire. We also know that it's brought outside after it's pumped up with particles, and it's 35 °C outside, but if you turn that into Kelvin and add 273, you should find that it's at 308 Kelvin. And then the final volume assume the volume of the tire actually increases to 365 milliliters. I left that off and had to add it just now to the description. So I'm going to add 365 to my graphic organizer. And now we are going to try to solve for P2. So this is not a reverse order final to initial. We're actually just going to do the change-ins from initial to final since we're solving for a final pressure. So the volume from initial to final, that's an increase. So I'm going to abbreviate increase with INC. The temperature increases also from the house to the outside. The number of particles goes from 10 to 15 because we added in 5 more amounts of particles. So that's an increase. And then we don't know that the change right now. We could speculate what the pressure change should be, but we won't really know until we go and think about the effect on the pressure conceptually. So make sure you guys are aware that we've got graphs in class that talk about things like volume and pressure, and that volume pressure graph had pressure on the y and volume on the x, but it was the inverse product. So it's the section up here where it's P times V. So when you look at the volume change, if there's an increase in volume, you got to think, what's the effect on the pressure? So conceptually, most people can think about our syringe background. When we increase the volume of a syringe, we've conceptually said there's more area available for the particles in that sample to increase and less collisions on those areas. So there's less force on an area because there's just less particles in the area location. And so that's conceptual, but if you look at the graph, if you increase the air or the volume, the pressure seems to decrease along that inverse curve. So the effect on pressure should be a decrease. When you look at the temperature versus pressure, that was a linear graph in Kelvin. Pressure versus temp. And that's also hidden up here in this algebraic version. Pressure in the numerator, temperature in the denominator, which represents a linear pattern. So we have temperature increase. Most people would already conceptually say if temperature increases, the particle speed increases, which leads to more vigorous force applied to a surface area, which should lead to an increase in pressure. And if you don't rationalize that out conceptually, you can look at the graph and assume as temperature increases, according to our previous data, the pressure should also increase based on the graph. So I'm going to put an increase here for pressure. And then finally, the number of particles increase versus pressure, and we have data from class that suggested that pressure compared to number of particles was also a linear line. Because it's zero number of particles, you should have zero pressure conceptually, because there's no particles to apply force on a surface area. So if we increase the number of particles or amounts of particles, the linear graph suggests that the pressure should increase also. So I'm going to put an increase. Now I'm going to build ratios out of the volumes, the temperatures, and the number of particles in order to get the effect on the 98 PSI, excuse me. So I'm going to start with the partner in crime that's missing. So 98 does not have its partner. So I'm going to start with 98 PSI, pounds for every square inch. And I'm going to start making ratios out of the volume. And the volume needs to be set up so that 98 doesn't get larger. So I'm not going to stick the 365 milliliters on the numerator. I'm going to put the 300 because we conceptually said that there needs to be a decrease. And you don't get a decrease if you put 365 in the top. You need to put the 300 in the top to give it a smaller outcome. And those are milliliters. So that one's done. I'm going to make a relationship now out of the temperature changes. We said that it's got to increase the pressure, this change in temp. So now I'm going to put the 308 in the numerator because it's the larger number of the bunch, and it will give me a larger effect and lead to an increase in pressure. And that's in Kelvin. And then in the denominator, I'm going to put 295 Kelvin. And the temperature ratios are done now. As I move on to the number of particles, the change of the increase leads to an increase in pressure conceptually and graphically. So I'm going to put the 15 amounts of particles, and we've been using just AP for amounts of particles, compared to 10 amounts of particles, so that increase in particle amounts leads to an increase in pressure. And having the larger number on the numerator will lead to that influencing it to be larger in the end. So these values get very large on this example. So double check my work. I'm going to take 98 PSI multiplied all the way across the numerator, and all these units actually cancel through the act of division. So when I take the numerator all the way across, I got 135,828,000 PSI. And then when I take the denominators times each other, do not take the 98 down to the denominator. Remember, there's a ghost 1 hanging out under the 98. When I take 365 times the 295 times the 10, I got 1,076,750 with no units because they all canceled. And now if we simplify the relationship, I ended up getting 126 PSI, which reasonably makes sense based on bike tire manufacturers' recommendations. And in the directions it said the maximum recommendation was 125 PSI for the tire. Is the new pressure that the bike tire becomes more than expected or more than the maximum? It is by 1 PSI, so that's against the manufacturer's recommendation. So make sure you guys check your work, check my work, and check in next here for the particle diagrams. And since we're changing the number of particles on this example from 10 to 15 and the volume's changing, I'm actually just going to show you guys how to do the volume change alone. Or actually I'm going to keep the volume constant because I want to show that the number of particles has changed. So I'm actually going to do one version of this only. Let me clean the screen. I'm going to use the particle model to best show and communicate the changes that have taken place from the initial to the final. I know that the volume increases, but the problem is I also know the number of particles increase, and I know that showing both of those changes is a nightmare and not easily communicated. So I'm going to treat the volume of the microvolume as a microvolume, a tiny sample of the bigger gas sample inside the tire. So I'm not worried about showing the actual volume change itself. However, I will show the change in the number of particles and the temperature change. So in the initial state, I have some amount of particles, 10 amounts, but I'm just going to represent that with like 4 particles. I know the temperature is less in the beginning, so I'm going to draw a average EK arrow with a smaller arrow, knowing that I got to increase it in the next state. So in the next state, instead of showing the volume increase, I'm just going to show a constant volume, and I'm going to show the number of particles increasing here. And the temperature must increase as well, and that means the average EK increases. So on one hand, I suppose we could have tried to change the microvolume into a larger version to show the volume change, but then showing the increase in number of particles isn't necessarily obvious either. So pause the video, rewatch it as needed, work on any assisted worksheets that you guys have from class, and if you got questions, come see me.